Assalamu alaikum dear students. A2 Physics 9702. This is chapter 17 and the topic oscillation of the chapter name is oscillation, and here we are going to discuss the resonance. Whenever you will talk about the oscillation, of course there are a number of terms you have to learn, and I have written few of these terms which are related to this topic, which is the resonance. First of all, we have one term which is free vibration. Free vibration. So how you will define this free vibration? Simply you can say that where a system is given an initial displacement and then allowed to vibrate freely, and this oscillation is the free oscillation. Yani suppose if you have a pendulum and here you have the situation like this pendulum is of a particular length. You are displacing this pendulum from its initial position, suppose somewhere here, from point A to B, and then at point B you will leave this pendulum. So what will happen? Of course the pendulum will move back, or the bob of the pendulum will move back to A, then it will move to C, as we have learned in the previous discussions that of course the oscillation is to and fro motion. So this is what is happening here. Now if you are not putting any more energy or you are not applying any force, then the vibration of this pendulum which you are just dealing here is termed as the free vibration. So remember this thing, that in case of free vibration you will just you can say displace a body at one point and then you will leave it. The rest is simple vibration. And what is the situation? Free vibration. So remember this point, that free vibration is the vibration where the system is given an initial displacement and then allowed to vibrate freely. Similarly, here we have another term after this free vibration. We have a term natural frequency. So remember this thing, that each and every body can vibrate, and whenever a body will vibrate freely, the frequency of that body will be termed as the natural frequency. So in case of free oscillations or vibration, the system oscillates at a set frequency which is known as the natural frequency of the system. Like I can of course give you examples, but for the time being I'm just giving you the definitions here, that what is the natural frequency. So if you have this pendulum, you are just displacing the bob once, and then you leave this bob at point B, and you are observing that the body is moving, or the bob is moving from point B to A to C, and then same is the situation, C to A to B, any simple oscillation. And the frequency this time will be the free frequency or free frequency, or simply you can say the natural frequency. So free vibration, and with this free vibration the term associated is natural frequency. So this is first thing. The second thing is that if suppose you have this pendulum and you are just pushing this pendulum again and again, so it means that each time you are feeding a particular energy to the system. So now the system is not vibrating freely, but it's a forced vibration. So how you will define forced vibration or oscillation? So simply you can say, when a driving force is continuously applied to make the system vibrate or oscillate. Of course, like suppose you have a situation of a swing here, and if the swing is moving freely, means only one displacement and then there is no more energy provided, then this is simply the free oscillation. But suppose in this case the mama is continuously putting some energy in and pushing the girl continuously, then it is the situation of the forced vibration. So this is something which is very important to understand, that when the driving force is continuously applied to make the system vibrate, this will be the forced vibration. As I said that if you have a pendulum and continuously you are feeding energy, then of course the vibration will not be the free vibration, but it will be the forced vibration or oscillation. Here we have another very important term, which is the driving frequency. So what is the driving frequency? The push by the mama in this case is actually the driving force. So the simple thing is that the frequency of the push, or the frequency of the force which the mama is applying continuously here, will be the driving frequency. So simply what you can say, in case of forced vibration, the object that provides the driving force moves at a certain frequency. This frequency is called driving frequency. So in our example, the mama pushing the baby, simple thing is that who is pushing? Mama is pushing. So simple thing, you can say that the driving force is coming from the mother, and the frequency of this driving force will be termed as the driving frequency. So this is something very important to understand, that at least these four definitions you have to learn whenever you are going to describe the resonance. Now, what is the resonance? Basically, here we have not discussed anything for the time being, the resonance, but four definitions. So now what is the resonance itself? As I said that you have natural frequency and different bodies which can vibrate. All these bodies are you can say carrying a particular frequency, and that frequency will be the natural frequency of the body. Like suppose if you have a metal baseball and a wooden bat, the sound will be different when you will drop these two on the floor. So each one has its own frequency, and this will be the natural frequency of this body, or of course in this case natural frequencies of these bodies. Here actually if you will go for the resonance, as I said that first of all you have to consider the natural frequency, and of course then you have to consider the driving frequency to understand the situation of the resonance. For the pendulum, I have given the formula for the natural frequency. If you have a mass spring system, then you have another formula for the natural frequency. Like in pendulum, the length of the pendulum and the value of G will give you the idea that what is the natural frequency of a pendulum. Similarly, if you have a spring, suppose, and this spring is attached with a body, or a body is attached with the spring, and you are just observing the vibration of this or oscillation of this mass spring system, then the frequency over here of this body will be given by this formula, where K is the spring constant and M is the mass of the body attached with this spring. So these two very important you can say cases and examples. And of course, as I said, that each and every body has its own frequency, natural frequency, depending on its dimensions and other factors. So what is the resonance? So simply the resonance you can define in this way, that the resonance occurs when force vibration matches an object's natural frequency. So this is very important. Then basically resonance is a phenomena which will occur when the force vibration will be equal to the object's natural frequency. Yani you have suppose the driving frequency as Fd, and you have a natural frequency F naught. When F naught will be equal to Fd, you will see that the body is moving with the greatest amplitude, and you can say that the resonance has occurred, or the body is in the, you can say, phenomena of resonance, or is resonating. So different ways to represent the same thing, but simple point is that when the forced vibration becomes equal to the object's natural frequency, or the force frequency will be equal to the natural frequency, the body will resonate. Oscillations grow in amplitude due to synchronized transfer of energy into the vibration object. So this is very, very important, that when you are applying the force again and again, and you are feeding the energy again and again into the system, so what will happen? Oscillations grow in amplitude. Of course, the amplitude of the oscillation will increase. So this is what we are saying, growing with the you can say feeding of energy due to the synchronized transfer of energy into the vibrating system. In this case, you have suppose a swing and the mama is pushing again and again. So the forced vibration of the mama is nothing but FD, and this you can say pendulum or swing has its natural frequency. So when it will be equal to each other, you will see that the swing is vibrating to its maximum amplitude, and what you will say, the swing is in resonance, or the swing is resonating. So this is what we have as far as the resonance is concerned. Here you have to remember these few points, like pushing a swing is simple example of using a drive force to produce oscillation. So I have given you this example before as well. So what we are saying here, that when you are pushing a swing again and again, you are basically driving or pushing the you can say swing in this case, or driving the oscillation. So this is basically the forced vibration you are producing. The frequency of the pushing force, as we have just discussed, the frequency of the pushing force is nothing but the driving frequency. When this matches the natural frequency of the swing, the greatest amplitude will be reached by the child on the swing. So we have already discussed this point, that here suppose you have the driving frequency along x-axis, and here you have the amplitude along y-axis. So what you are observing, that when you are increasing the value of your driving frequency, the amplitude of the swing is increasing, and when you will have a situation of your natural frequency is equal to the driving frequency, then you will see that you have the maximum amplitude. So swing is vibrating with the maximum amplitude, and what you will say, the swing is resonating. If the driving force is higher or lower, the amplitude attained will not be the high as before. As you can see that if this driving frequency is less than the natural frequency or greater than the natural frequency, then the amplitude will not be the maximum, but it will be more than or less than. Yani of course here you have the maximum. So more frequency, yani greater than f naught, will do the same thing as the lesser frequency was doing. Yani when your driving frequency is less than natural frequency, or when your driving frequency is greater than natural frequency, your amplitude will not be maximum. But when fd will be equal to the natural frequency, at that moment only you will get the maximum amplitude. So this is what we have. Now here we have one simple question. Any simple thing is that when we of course are not providing the frequency, or the driving frequency is less than your f naught, that is, I think is logical that you are not getting the maximum amplitude. Yani your driving frequency is less than the natural frequency, then it is okay. Of course, the amplitude will not be the highest. But what about this point, that when your driving frequency is greater than f naught, then why this amplitude is decreasing? So this part is, I think, you can say is very important here, that why this part, when we have the frequency greater than, or the driving frequency greater than the natural frequency, then why the amplitude is decreasing. So this is very, very important. But it's not very difficult to understand. Here, one thing which is very important, the point is that, like, suppose you have a body, and this body is going from, suppose, position say 1 to position 2, and then it is coming back. Your force, which is the driving force, is acting on the body. So what will happen? Actually, the thing is that when the driving frequency, or when your force which you are applying here, driving frequency is greater than F naught, it means that what will happen? When the body will reach somewhere here, this body is somewhere here, and your frequency is greater than the natural frequency. So what will happen? You will be somewhere here, and your force is, you can say, disturbing the complete oscillation. Your force is not allowing the body to come back to position 1. So what is happening? The body was trying to come back to position 1, but your force was somewhere here. So what will be the situation? The body will do some work against your force. So because of that, the energy will be lost from the system, and because of this situation, the amplitude decreases. So this is very, very important to understand that, suppose in this case, the swing, suppose the swing is somewhere here, and your frequency is greater than the natural frequency. So what will happen? The swing is trying to come back to its original position, but as your frequency is higher than or greater than the natural frequency, so you are coming somewhere here, or your push is somewhere here. So what will be the situation? Your force, I can write in this way, that the driving force basically is just opposite in the direction of oscillation. As I said before, that you are somewhere here, and the force with the driving force is somewhere here. So they are just opposite to each other, and because of this, the system here, you have basically the ball is or the bob is the system. So what will happen? The bob or the ball will have a force opposite to its motion, yani the ball has to work against your force, the driving force. So what will happen? The system will lose energy. So simply you can say that what will happen? This will be the situation, yani there will be a decrease, ultimately the decrease in the oscillation. So in both the cases, whether your driving force is greater than or less than the natural frequency, the amplitude will not be maximum. So this is very, very important to understand that what is happening in this case when your force or the driving force is greater than or less than the natural frequency, the amplitude is not the maximum amplitude, or the body is not, you can say, in the situation of resonance. So when the resonance is occurring, the frequency of the body, any natural frequency of the body, must be equal to the driving frequency. So this is very, very important. Here we will come back to the other points as well, but just to give you the idea, like here we have the animation. Here we have one animation in which you can see 3 balls, blue, pink and yellow, and you can see here that the spring constants are 50 for blue. Mass of all these balls are basically the same, but over here the spring constant of blue is 50, spring constant of pink is 100, and spring constant of yellow is 200. So if you will go back to the calculation, as I have already explained this thing, that the natural frequency you can calculate with the help of this formula, that F naught is equal to 1 over 2 pi square root k over m. So for blue, the K is nothing but 50, mass is 2 kg. Basically, this is K, and actually you have to recall that F is equal to Kx. If you can recall this simple formula, the Hooke's law, and you know that K is nothing but F over X. So how you will calculate? Of course, you will apply a force, and you will see that what is the situation of the displacement, or the you can say deformation. So over here, of course, the unit of F is nothing but Newton, and the unit of your displacement or deformation is meters per meter. So simple unit of K is Newton per meter. So this is what we have as far as K is concerned, but in this case K is 20. When you will calculate the F naught for your blue ball, you find that it is 0.8. Now check the situation of your you can say system over here. You can see all these blue, pink and yellow balls are attached with the system, and you can vibrate the system. But this situation is that when you will bring the force frequency somewhere here, which is 0.8 something like this, then what you will observe, this is very important. Let's see what is happening here. All these balls are vibrating, but as the natural frequency of your blue ball is 0.8, and what you have set here, the force frequency, which is equal to 0.8, so what you will see that the blue ball will vibrate with the maximum amplitude. And this is what you can see, that here you have the reference line, and reference line means that you just want to know that what will be the maximum amplitude. So simple thing is that of course we can move this point up and down as well, but if we are keeping this reference point, so what you can see here, that with this 0.8 frequency, all of them are getting the same frequency, yani force frequency for all of them is 0.8. But as for the blue ball, you can say and see the calculated value of the natural frequency is close to 0.8. So you can see here that the blue ball is resonating, or the blue ball is vibrating with the maximum amplitude. So simple thing is that you can say the blue ball is resonating, and you can see the other two balls, any pink and the yellow balls, are not vibrating with that maximum amplitude. Now let's see again what we have here for the pink ball, the same calculation, and you are getting 1.13, because here you have the spring constant as 100 Newton per meter. 100 Newton per meter. Of course, mass is same, which is 2 kg. So the natural frequency of the ping ball is 1.13. So what we can do, we can now reset the frequency 1.13 somewhere here. This is the frequency. Now let's see what is the situation of these three balls. The natural frequency of your ping ball is 1.13, and you have provided this frequency, and force frequency is also 1.13. So what you are observing now, you can see the ping ball is vibrating with maximum amplitude. Again the same point, again the same thing, we have provided the same energy or same frequency to all of them, but only the ping ball is vibrating with the maximum amplitude. Why? Because we can say that this ball, any ping ball, has this situation of F naught is equal to Fd, and force frequency is equal to the natural frequency. So what is happening? Simply you can say that the ping ball is resonating. The ping ball has the maximum amplitude. So this is very important, that the ping ball now is resonating. I hope you are getting what I am saying. The natural frequency when becomes equal to the force frequency, at that moment only the body will vibrate with the maximum amplitude, and this is what we are observing here. And now we want to set for the third situation where we have the yellow ball, and this time the K is nothing but 200 Newton per meter, mass is same, which is 2 kg, and the calculation says that we have the natural frequency as 1.59. So what is the situation here? 1.59, we can set now 1.59, and we will observe that what is happening this time. 1.59, close to 1.59, somewhere here we are. And now what will happen? Of course, this is not just equal to 1.59, but very close to 1.59. And what you will observe this time, that the yellow ball is vibrating with the maximum amplitude. Again, please remember that all these three balls are getting the same frequency because they are attached with the same rod. The rod is vibrating with 1.59, but as 1.59 is the forced frequency, which is equal to the natural frequency this time of yellow. So simple thing is that the yellow ball is oscillating with the, or yellow bob is oscillating with the maximum amplitude, and you can say that the yellow ball is resonating this time. So this is very, very important. And what we are observing, again the same thing, that our pink ball and blue ball are not vibrating with that amplitude. So the simple point is that the resonance is something, a phenomena when the natural frequency of a body becomes equal to the force frequency, then the body will vibrate with the maximum amplitude, and we will say that the resonance has occurred. So this is very, very important point to remember. I hope you got the point. Here, of course, we have discussed in the last lecture the concept of damping. And if you want to know the damping, you have to go to my lecture of damping as well. And of course, this is very important to remember. For the time being, I'm just telling you the damping is nothing but taking energy out of the system. So something like this we can simply define. So if you will have a damped system, then what will happen? The energy of the, you can say the energy which you are feeding will be given off in one way or the other, or you can take the energy out of the system when you are damping something. So like suppose if you have the practical situation, even a simple pendulum, if you will consider, and as I said before, that you are thinking that you are taking the bob to position, suppose from A to B, and you are leaving the pendulum at position B. The pendulum or bob is going back to A, then is moving to C, and then it is coming back. So what is happening? The pendulum or the bob is vibrating between point C, A and B. So this is the natural situation. But even in this case, you know that the air resistance you have, so it means that the air is basically acting as a frictional force. So the air is taking energy out of the system. So you can say that the damping of the system is taking place. So this is very, very important. So here I just want to, you can say, give you some idea that what is the situation of the damping. Here what we can say, what we can write, if the driving frequency is close to the natural frequency, the amplitude can become quite large, especially if the damping is small. So here you can say and see that this is the situation of the small damping. Yani if you are considering an example like pendulum where the only air friction is acting as a damping force, so you can say that the resonance will give you a very high amplitude. So this is very important. But if you are doing something special to take energy out of the system, and because of that you have a large damping, then what will happen? You can see here that the amplitude of your resonance is not that high. Here you can see the amplitude, here you have the greatest, and of course the amplitude is decreasing for more and more damping situation. So remember this thing, that for small damping sharp peaks you will get, and for large damping broad peaks you will get. Yani of course the in the frequency which is the natural frequency, here you can see that this is the point. Suppose this is the point, if you will take suppose the highest one, so you can say that this is the position of the natural frequency and the driving frequency. But here you can say that this point is the point where we are getting the maximum displacement or maximum amplitude. So it means that for this situation, yani for the large damping thing, the driving frequency will be less than this driving frequency. So this is very, very important, that the broad base shows that you are getting the resonance situation before the time or before this small damping thing. So be careful of these points. In the coming lecture I will explain few other points as well. So this is part 1 of your resonance, you can say, and inshallah in the next discussion, because the discussion is becoming you can say long, so I'm just stopping the discussion at this point. And if you are of course new on my channel, so subscribe this channel and press the bell icon as well. Inshallah in the next part I can say that this is lecture 5 resonance, and I'm writing here part 1, where we have explained the resonance. Of course we have first of all explained free vibration, natural vibration or natural frequency, and then we have force vibration and driving frequency, and then the concept of resonance we have discussed. We have discussed that how the resonance will occur when the natural frequency will become equal to the force frequency. And of course I have given you one example with the help of the animations as well. So inshallah in the next part I will show you a few more things about the resonance, and then uses and the advantages and disadvantages of the resonance we will discuss. So as I said, that if you like this discussion, share and like the channel, and of course in the next part I will explain a few other points of the resonance. Till then, Allah Hafiz, take